This is the Chapter 5 whiteboard lecture on volcanic eruptions, and it will cover PowerPoint slides number 1 through 26. In the last chapter, we covered magma that stays below ground and slowly crystallizes over time, creating plutons. So in this chapter, we're going to look at magma which erupts, which is then called lava. And this is when extrusive and volcanic rocks are created. So there are 3 different parts to a volcano. The first one is the vent, and the vent is actually a crack in the ground where lava erupts out of the surface. So we often think of a volcano as its cone, but the cone has to be built over time. So the vent is the first thing that happens. You just have a crack in the ground and lava begins to erupt from that crack. The material that is erupted creates this cone. It builds the cone around the vent. We call that a volcanic edifice or just a cone. That's the part of the volcano we see from outside. But inside, there are also pipes. This is the main conduit in which magma rises up and then erupts. We also have craters that can form at the top of a volcano, and then calderas, which are actually associated with larger explosive eruptions that take a lot of material of the pre-existing cone away. There are 3 factors that play a role in deciding whether magma will stay below the ground and crystallize into a plutonic rock, or will erupt and become an extrusive volcanic rock. We're going to cover each of those 3 factors, and then we're going to look at how they work together. The first factor is buoyancy. So this is the tendency for a less dense material to move up if it's surrounded by something more dense. So in general, and with the important exception of water and ice, liquids are less dense than solids of the same composition. So if you have a mafic magma surrounded by mafic rock, that magma will be less dense than the rock and will have a tendency to move up. And that's buoyancy. However, when magma starts to move up, it is moving into a cooler environment. Remember, it gets hotter the deeper you go down into the earth. So as the magma moves up, it also begins to cool down. And when magma cools down, it begins to create crystals, right? Crystals of different minerals begin to grow in that magma as its temperature decreases. At some point, when we get to about 50% crystallization, we have what's called a crystal mush. So at that point, 50% crystals and 50% liquid. And the magma at that point becomes so thick that it will no longer move up. So the process of getting magma up to the surface is sort of a race between how fast it's cooling and how fast it's actually rising. The second factor involves dissolved gases. All magmas contain gases or volatiles that are dissolved in that liquid rock. They include water vapor, and that's one of the reasons why you see steam coming up from a volcano. Carbon dioxide, nitrogen gas, sulfur dioxide, which is what makes volcanic eruptions stinky. They smell like rotten eggs. And then chlorine gas, which is actually kind of dangerous, although usually there isn't enough of it in a concentration to be dangerous if you're just around a volcanic eruption. The amount of dissolved gas varies by the composition of the magma. So mafic magmas have the lowest amount of dissolved gas, while felsic magmas have the highest amount of dissolved gas. And you can see in general it's under 10%. So what happens to those gases as the magma begins to move up toward the surface? Magma at depth is under a lot of pressure from overlying rocks. And when you move it up towards the surface, it's under less and less pressure. And what happens to those gases is then that they come out of solution and form bubbles. This is the same thing that happens when you open a soda. Sodas are bottled under pressure, so they can put additional carbon dioxide dissolved into the soda. So when you open a soda, you're decreasing the pressure, and bubbles of carbon dioxide then form in the soda and begin to bubble up towards the surface. Same thing happens to magma. The more magma moves up, the less dissolved gases can stay in the magma, so they come out of solution, they form bubbles in the magma. The third factor is simply the viscosity of the magma. Viscosity is a measure of a fluid's resistance to flow, so you can think about it as thickness, how thick the magma is. And there are two factors that affect the viscosity of magma. One of them is silica. Remember, that's the amount of silicon and oxygen in the magma. So the higher the silica is, the higher the viscosity is. So more silica is going to mean a thicker magma. Temperature has the opposite effect. Higher temperatures decrease the viscosity. So a higher temperature magma is going to be more fluid or thinner. So it's a combination of these effects that actually decide whether or not a magma is going to erupt and whether it's going to erupt quietly or explosively. So first of all, we have buoyancy, which is causing the magma to move up. That decreases the pressure, which causes gas bubbles to form in the magma. And then the viscosity determines whether the magma releases those bubbles or traps them. So in a very thin magma, the bubbles of gas can move up to the surface, basically the outside of the magma chamber, and those gases get released out into cracks in the rock. But in a thick magma, those bubbles actually can't move fast enough up to get to the outer edge of the magma, and so they end up getting trapped in the magma. And as more and more of them get trapped, they begin to exert pressure in an upward motion. So if the bubbles escape, then the magma can erupt quietly when it finally reaches the surface. It may have some bubbles that are near the surface. You may see a little bit of bubbling or fountaining, but the eruption itself will just be a quiet one where lava just flows out of the vent. But if the bubbles get trapped, they begin to push upward against the overlying rock. And then the magma can explode from depth. So it can actually take part of an existing cone off in that explosion. So this is just a summary slide showing the different characteristics of the magma types. So we don't have ultramafic on here, remember, because ultramafic no longer forms. The Earth is not hot enough to make ultramafic magmas. But we can see for mafic magma, for instance, that we have a high temperature magma. Remember that mafic magma has those high temperature minerals melted in it. And so therefore its temperature must be high. It has about 50% silica, and it had the lowest amount of gas content. If we move over here to the felsic magma, we have a magma that only has the low temperature minerals in it, so it doesn't have to be very hot to have melted those. It has about 70% silica, and it has the highest gas content. And then for the intermediate, we are literally mostly just intermediate between mafic and felsic. So I want to talk a little bit about how the numbers that we've talked about, the percent silica here, is just one number sort of in a central area of the type of magma. But in reality, all of these magmas have a range of silica content. So the mafic magma here has this range. felsic magma has this range, and the intermediate magma is in the center. But notice how the intermediate magma can sometimes here be more mafic, more similar to a mafic magma. But sometimes you can have an intermediate magma that's closer to this, and it's more similar to a felsic magma. This means that the intermediate magma actually can change its behavior depending on whether it's more mafic or more felsic. So a mafic magma has a very low viscosity. It's very fluid. This is because it's hot. Remember, increasing temperature meant you decrease the viscosity. The magma was more fluid. Felsic magma, on the other hand, is cool and it has a lot of silica in it, so it is very thick. It has a high viscosity. This means that for mafic magma, we're going to have pretty effusive or quiet eruptions. We don't have a lot of gases to trap. We don't have a thick magma, so it's not going to trap any gases that are in there. And it's very hot. So it's very fluid. It just flows out of the vent very easily. The felsic magma is the opposite. It's so thick that it almost never erupts. It actually often cools below the surface. It becomes that crystal mush and just rises a certain amount but can't make it to the surface. The intermediate magma, on the other hand, sometimes erupts quietly or effusively when it's close to a more mafic composition. But it also can have very explosive eruptions when the composition is more felsic. So intermediate magma can actually have both kinds of eruptions. So we have effusive over here. We have both effusive and explosive in the middle. And here we have explosive if it does erupt, but it rarely erupts. So we're going to talk about the two main categories of eruptions, effusive and explosive. We're going to start with the effusive eruptions. So again, here we're talking about mafic magma, low viscosity, very fluid, high temperature, very few bubbles to trap in the first place. You can, in the very beginning of an eruption, get something called fountaining, which is shown in this photo. This is because at the very top of the magma, you may end up with some bubbles being trapped. It's not enough pressure to cause an explosive eruption and actually take off any pre-existing cone, but it can bubble up like a water fountain, which is why it's called fountaining. The eruptive product. So eruptive product is a term you're going to see in the next few slides as we talk about volcanic eruptions. In this case, it is lava flows. So that is what is coming out of the volcano. The speed of lava flows can vary, but it can get up to 20 miles per hour. So that is something that you can easily get away from, even on a bicycle, certainly in a car. So it's not dangerous to people, but it is very dangerous to property. So that's its biggest hazard. You can't move your house or the shopping center to get it out of the way. And the big island of Hawaii often has volcanic eruptions that overtake areas that are houses or cities, etc. There are two types of lava flows. So again, that's the eruptive product of effusive eruptions. And they are very different from each other in the way that they look, and that comes from characteristics of the lava itself. So these were named in Hawaii, so they have Hawaiian names. The first one is called a pahoehoe flow. It has a very smooth, ropey surface, as you can see down in this photo. And then we have an aa flow, which has a very rough, jagged surface, as you can see here. This one down here is a pahoehoe flow, so the aa flow here is sort of flowing over an older pahoehoe flow. So the reason that these two look so different from each other is because the pahoehoe flow forms when lava is very hot. That allows a very thin skin to form on the surface of the lava flow. The lava is very hot inside, so that skin that is in contact with the much cooler air is still very thin. As the hot lava continues to push forward inside, that skin will stretch and flow, kind of like fabric. And so it forms a very smooth surface, but it has those sort of wrinkles of fabric. There are some videos in the additional resources on the Eagle page where you can see these lava flows forming. The Ah flow, on the other hand, forms after the lava is cooler. So you still have a thick lava flow. It's still pushing forward. But now you're creating a much thicker skin because the lava itself is not as hot inside. And that thicker skin cannot stretch. Instead, as the lava pushes forward, that thicker skin breaks into pieces and creates that jagged surface that we see. So these lava flows are actually part of the same flow. What happens is that when lava first erupts from the vent, it's very hot, and so it creates a pahoehoe flow. But over time, that same flow begins to cool off, and the skin on top of it gets thicker, and therefore it begins to break up. So we tend to find pahoehoe flows very close to the vent where the lava was still very hot. And then Ah flows are found farther away from the vent after the lava has cooled off. Another type of lava flow that we see are pillow lavas, and pillow lavas are specifically associated with forming underwater. The additional pressure from water compared to air pressure, water pressure is higher, actually causes these kind of pillows or sausage shapes of lava to form. This is another thing you can see in a short video clip that's in that additional resources. You can see the pillow lavas forming. So moving on to explosive eruptions, we have a different eruptive product here. Instead of a lava flow, we have pyroclastic material. So the pyroclastic material includes basically exploded material, material that has been broken into pieces from both the magma itself and from any pieces of pre-existing cone that were caught up in the explosion. Magma, remember, is a silicate liquid, so it's like exploding a glass. You make very, very tiny shards of glass, which we refer to as volcanic ash. These are very dangerous to breathe in. If you try and wipe volcanic ash off your car, the tiny shards of glass can basically ruin the finish. Very bad for your lungs, obviously. So people tend to wear some sort of mask whenever there is a lot of volcanic ash in the air, if they're in an area where you've had an active volcano, which has an explosive eruption. We have other sizes. Lapilli are sort of pea-sized. We can have volcanic bombs, which are pieces of that magma that didn't get exploded into small pieces. So they have this kind of roundish form because they were actually liquid and then they came out as a larger piece and cooled quickly. And then we can have volcanic blocks, which are usually pieces of the pre-existing cone that have been broken up, and they can be as large as a car. In addition to these pieces, you also have very hot gases. So those gases that were dissolved in the magma also are immediately released, right? That's what the bubbles were that were causing the pressure that caused the explosion to happen in the first place. So we have a mixture of very hot gases mixed up with all of this debris. There are three specific rock types that we didn't talk about in the last chapter, igneous rocks, that only form from explosive eruptions. So we have tuff, which is when you have a lot of very fine ash that accumulates on the surface from an explosive eruption. We can also have a welded tuff, which is when that ash is hot enough that the little tiny glass shards begin to weld together. or melt together. So you can see in this photo of the welded tuff how you have kind of layers forming, and those are layers. That layered effect is from the melting of the glass together and how it welds together. And then we can have a volcanic breccia. Breccia is just a word that means broken pieces. And so here you have a rock with a lot of broken pieces and then ash and other stuff around it that has sort of cemented it together. There are three types of explosive eruptions, so we're going to talk about each of those types. The first one is referred to as an eruption column. This is when the pyroclastic cloud, which is a mixture of the pyroclastic material and the hot gases, moves straight up from the vent as illustrated in this drawing. So there is energy from the explosion itself, and then this material is also buoyant because it's very hot. Eventually, however, it cools down, and when that happens, it tends to spread out and make something that looks a bit like a mushroom cloud. Um, the biggest danger from this kind of eruption is the ash fall. So basically, you're going to end up with all of this stuff eventually falling out of that cloud as it loses its buoyancy, and it's going to accumulate in layers down here on the ground. Some pictures of eruption columns. So you can see that basically this material has moved up. It's beginning to spread a little bit here at the top. Additional pictures, again, this material is moving up, coming up here. And then these photos are illustrating just how devastating it can actually be. While this stuff may look like wood ash, silicates are much heavier than wood ash. And so when you accumulate large thicknesses on buildings, it causes them to collapse. And it's also very hard to clean up. So the second type of explosive eruption is called a pyroclastic flow. It was first described by the French, and so it also goes by the term nuée ardente, which means glowing cloud in French. There's actually an accent over this E to be correct about it. This is when the pyroclastic cloud, instead of moving straight up from the vent, actually flows down the cone. This happens because the energy from the explosion and the hot gases is countered by the amount of material that's in the cloud. So if there's too much material compared to the proportion of gases, then instead of moving straight up, the cloud kind of comes out of the cone and then flows down the side. So these are some photos of pyroclastic. In this photo, you can see very large cloud basically going down here into the ocean. In this photo on the other side, you can see two pyroclastic flows coming down here, and we also have an eruption column moving up, and this is pretty common. These two types of eruptions can happen at the same time. You can get some material that has that energy to go up, and then other material that doesn't have as much energy and it flows down the side. Pyroclastic flows can move up to 100 miles per hour. So remember we talked about lava flows. They can only move about 20 miles per hour. So easy to get away from. But pyroclastic flows are very fast. And if you're in the path of one, it's very difficult to get away. They can flow up to 60 miles from the cone. Not all of them go that far. These are upper limits, the 100 miles per hour and the 60 miles. Again, some photos of pyroclastic clouds. This is from Mount Pinatubo in the Philippines, and you can see there is that Jeep down there, which most likely did not make it because this would have been moving so fast. Here we have again some material moving up and then material moving down the sides as well. So the third type is called a lateral blast. And this is a very specific type of eruption that happens when there is some part of the volcanic cone that is more fragile and the magma inside the cone gets suddenly exposed to air pressure. And so the explosion is much more violent. So we first described this and first saw of it in the 1980s Mount St. Helens volcanic eruption, which is Mount St. Helens is in the Cascades range over on the coast of Washington and Oregon. So in that case, there was a pre-existing fault which had not been mapped. So the geologists who were monitoring the volcano did not know about the fault. That caused a landslide as magma moved up into the cone. And because the magma is suddenly exposed to air pressure, instead of the explosion happening while there is still rock on top of the magma, you end up getting an explosion that moves at the speed of sound or more. So 760 miles per hour is the speed of sound, but we're talking not about moving miles, certainly not 760 miles. So we can, that blast can cover 1 mile in about 5 seconds. This also leaves a blast zone, as you'll see in some photos we'll look at for Mount St. Helens. So these diagrams illustrate what happened at Mount St. Helens. There's a dashed red line in this first image, which was the original shape of Mount St. Helens. As the magma here began to move up into the cone, geologists noticed that this side of the volcano, which was the north side, was kind of pushing outward or bulging outward. And it was bulging outward at about 5 feet per day, which is, geologic things tend to move very, very slowly. So 5 feet per day was a very significant change in the shape of the volcano, in the shape of the cone. So we didn't know about the fault that was there. And what happened is the magma pushing on this rock caused the fault to activate. And so the outer part of the volcanic cone slid down in a huge landslide. That basically allowed this magma to be exposed to air pressure, which caused an enormous explosion out this way and continued landslides allowed even more magma to be exposed. And then after this had happened, you ended up still having explosions that basically removed that entire top of the volcano. This all happened incredibly quickly, right? So 8:32 a.m., 8:33 a.m. This is a photograph in the back of what Mount St. Helens looked like before the eruption. And then down here, they're comparing it to what it looked like very soon after the eruption. So right here is a lake called Spirit Lake, right at the base of the volcano. After the eruption, Spirit Lake was completely filled with debris. And all of this cone basically is gone. These are another couple pictures of what it looked like in the area of the park, because Mount St. Helens is a national park after the eruption. You can see all of the trees that have been basically mowed down by the blast, which is why we call that a blast zone. Here is a car that has been buried. There were about 60 people who died in this eruption. One of them was the geologist who was monitoring the volcano for the USGS. He was about a mile away from the volcano, and he was due north, which is exactly where the blast occurred. He radioed to his colleagues that he could tell something was happening, but that was the last. I mean, it took 1 second for the blast to reach him.